Good morning. So today's lesson is actually a very short lesson. I just want to give you some examples. There is nothing that I can teach now. So if you remember, we talked about differentiation, the process that takes us from the notion of the derivative, and so from the function to a new function, which is called the derivative function. Differentiation process is that process that do this for us. And then I told you that there are three generic rules that we learned about, which does not depend on a particular function. And one rule is that if you have a multiplicative constant, if you have a constant multiplied by a function and you want to differentiate it, you do not touch the constant, you just differentiate the function and multiply the constant into that result. If you have the sum of a bunch of functions and you want to differentiate them, I have written it only for two functions, but you can improve if you extend it to more number of functions. So in that case, if you want to take the derivative of the sum, you take the derivative of each function and then add the results. And similarly, if you have to subtract the difference of two functions, if you want to differentiate, you differentiate each one of them and subtract the results. And then here, this is a table that so far we learned about. If I have a constant function, the derivative is always 0. If I have a power function, a power function is a function whose base is x, but the exponent is a constant c. In that case, if you want to differentiate that, this c goes down, and then you write x to the power of 1 unit less. These ones that I have written in green, I expect you to have them in your memory. They are not given in the formula sheet. All these formulas can be derived from this one single formula. So if I choose c equals to 1, this formula gives me this line. If I choose c to be minus 1, x to power minus 1 is the same as 1 over x. If you do the same thing and simplify it, you will get this. And if you take x to c to be 1/2 and do this formula simplified, you will get this one. I really recommend you to memorize that, especially this one and the last one. Okay, so now the simple example we did before, so let me just increase the level of the difficulty of the example this time. So these are the functions that we can differentiate only based on these rules. So what you need to learn is to change the form of the function if necessary to be able to match the parts of the function with the given table there and then use the formula. So that's the general strategy to solve those problems. Okay, so let us just try to do these. So if you want to differentiate this function, so let me start from here. So number 1, so we have the derivative of this one. So here, before doing the differentiation, I do not need to change this one if you have the last formula in your memory. But the third root of x, I do not have it in the table directly, so I have to change its form. So this tells me that before starting differentiation, let me rewrite this in a slightly different way. 2 square root of x, because I have it in my memory, I do not change it, okay? But this one, I change it, x to the power of 1/3, and then 2x squared, and then minus 5x plus 1. Now I differentiate. This 2 is a multiplicative constant, so I will write it there. And then I differentiate this part, which is the last row in the form in that table, which is 1 over 2 square root of x. And then here, I use the second row of that table, but I give the rule of constant c to 1/3. So 1/3 goes down, x to the power of 1/3 minus 1. So this 1/3 minus 1, I expect you to do it in your head. Yeah, so it's minus 2/3. It's minus 2/3. And then this 2 goes down. This is a multiplicative constant. I do not touch it. This 2 goes down. X to power 2 minus 1, which is 1. And here The multiplicative constant, I keep it. The derivative of x is in that table, so it is 1. And do not write it, or if you want, you can write multiplied by 1, and the derivative of 1 is 0. And then try to simplify it a little bit. So this 2 and that 2 are cancelled, so I will get 1 over square root of x. This is plus 1 over 3 is in the denominator. I bring it down, it becomes positive 2/3. Yes, 1 over x to the power of 2/3, but I prefer to write this as the third sign, so this becomes the third root of x squared. So this becomes the third root of x squared, and then 2 times 2x is 4x, and then I have minus 5. So that would be the final answer in its simplified version. Any questions? Okay, I want to pause recording and give you a little bit of time to think about these ideas, and then I will change the type of the example to other types of the examples that you see in the book. So I pause recording, wait for you 5 minutes. Okay, so let us continue. So what is your opinion about number 2? Because, of course, I told you this is the product of two functions. In Math 4, you will also learn, you will add 2 more rules here in this purple color. One is called the product rule and one is called the quotient rule. But here we do not have them, so you need to find a way not to use them. Okay, so what I'm supposed to do, it's a product of 2 functions. But don't make this mistake, at least, that you take the derivative and say that I take the derivative of this one and the derivative of this one and multiply them. That would be wrong. Okay, so if I want to do it, I have to write it in a form that I can somehow use that information up there. So then I don't think it is hard to say what to do. Yes, what I should do? I expand that. So I just multiply that. So first of all, before the differentiation, I change the form of my function by multiplying this. So this becomes 2x squared times 1. And then 2x squared minus this is minus 6x cubed. And then this becomes plus 1 minus 3x. This is one of those cases that I think it would be better to do it very fast. Yes, I think it's very easy for you. So 2 goes down, but it is multiplied by 2, so it becomes 4x to power 1 unit less. 3 goes down, multiplied by 6, becomes 18x to power 1 unit less. The derivative of 1 is 0, and the derivative of minus 3x is what? What is the derivative of minus 3x? What is that? Minus 3. So that is the answer to this problem. So for the next one, it's also a product, and we also have a power 2. We haven't studied these rules. There's only one way for us to do it, and that is expansion. Okay? But here we also need to use the formula for the third sign to write it in the power form, because this is the only formula we have up there. So what I do, number 3, I would say that h of x is equal to 2 is just 2, but the third root of x squared can be written as x to the power of 2/3. And the next one, I use a squaring rule to expand that. So the first one squared is x to the 4th, minus 2 times the first one times the second one, plus the second one to the power of 2. Still, it is not enough because that's a product of 2 functions, so I have to expand it even more. So what I do, so let us just do some calculations in my head. So I multiply this term here, and then here, and then there, yes? When I multiply this here, this is a 2. This x to power 2/3, and this is x to power 4th. The bases are the same, so I write the same bases. And then I add the exponents. I hope that you can do it in your head, yes? Because 4 can be viewed as 12 over 3. 12 over 3 plus 2 over 3 is 14 over 3. Yes? And then I multiply this term here. 2 times minus 2 is minus 4. And then I have x to power 2/3 times x to power 2. I have to add this 2 to this 2/3. And it is also simple because for 2 you can write 6/3 in your head and add it here. So it becomes x to the power of 8/3. And then I multiply this one by 1, which is extremely simple. I just write 2x to the power of 2. I just repeat the term. Okay, first let me know if you have any questions up here. Yes? Understandable? And then everything is in the order, yes, in order. I use number formula in the second row several times, 3 times. Once here, once there, other time here. So h prime of x is equal to 14/3 goes down. Let us try to do it in our head. 14/3 goes down will be multiplied by 2. So 14/3 multiplied by 2. Still, I see some students multiply here and there. No, this 2 means 2/1. So 2 should be multiplied by 14, 1 should be multiplied by 3. So that's just 28/3. But x to the power of 1 unit less. Okay, can you do it in your head? 14/3 minus 1, what's the answer? Yes? 11/3. It's 11/3. Now, this goes down, and minus 4 is there. When I multiply minus 4 by this number, which is now down, it becomes minus 32/3. X to the power of 1 unit less, which is 5/3. And then this 2/3 goes down, so it becomes what? 4/3. X to the power of 1 unit less. What is the answer? 2/3. Yes, it's minus 1/3. So this is the derivative. You can keep it like this. If you insist, you can go back to the third form, but it is not necessary. You can just stop. Okay. So these two I also want you to know. Again, in the future, you will learn the quotient rule in Math 4. So you can use that formula. But even if I know that formula, I know it, but I will not use it. I will use it exactly the way that I want to do it right now. So I mean that even in Math 4, you know about the quotient rule because the quotient rule is more or less complicated. Whenever you can avoid it, it is better to avoid it if there is a better way. So for example, here there is a better way. Can you tell me what to do? Of course, for you, this is the only way because you haven't studied that. So number 4, so s of x, first of all, I have to change how it looks. Because in this form, I do not have any formula there that I can use. So what is your suggestion? How can I transform it into a form that I can use that formula up there? Yes?
You can split out the fraction into 2x divided by
Exactly.
plus 1 divided by
Exactly. So I would write it as 2x/x plus 1/x. I hope that you understand what I have written here is exactly the same thing. Assume that I give you this and I ask you to write it as one fraction because the denominators are the same. So you write the same denominator and you add the numerators. If you do that, you will exactly get this one. So this is the only trick. Might be it is good to remember. Okay, but then I can simplify that. So I can simplify it 2xx. Just ignore this in your brain, and then this x and x are gone. So what is left is 2. And now you can ignore this one. This is 1/x. But 1/x is one of those special cases that I have in mind. Otherwise, you have to bring it up and write it x to power minus 1 and then do the process. But because we have it here, I told you those green ones are not in the formula sheet. So that's up to you if you want to remember. So if I ask you what is s prime of x, the derivative of 2 is 0. The derivative of 1/x is that line there. So it's minus 1/x squared. So s prime of x is just simply minus 1/x squared. And this is interesting. You see, I have two different functions, their derivatives are the same. Yes? Because the derivative of 1 over x is minus 1 over x squared. This is a different function, but still its derivative is exactly the same. But this cannot happen, okay, that much. I mean, don't think that these functions are quite different. These functions are not quite different. They can differ at most by an additive constant. Okay, so if I have this function, it might look very different from 1 over x, but this is not. This function is the same as 1 over x, the only difference is an additive constant. So we will study that later. If two functions have the same derivative, then either they are exactly the same, or at most they can differ by an additive constant, not more. Okay, we will, of course, this is not trivial. We will study it, but we will not be able to prove it. You have to wait for the university to see why this is the case. Okay, any questions so far? Okay, but for the sim one, this one is also now hopefully clear what we are supposed to do, yes? Again, that is a fraction. We haven't studied the chain rule yet. Sorry, the fraction rule yet. But what we do, exactly, I will apply the same idea here to this problem. So number 5, so t of x is equal to, I split it this time into 3 fractions. So this becomes 3x squared over 6x cubed, and then plus 5x over 6x cubed, and then minus 2 over 6x cubed. So this is the first thing we do. So let me also put a star here. So remember this trick here. And then a start simplification. 3 over 6 can be simplified as 1 over 2. X squared and x cubed are simplified. So this is just 1x. In principle, I should bring everything up, but because 1 over x is one of those exceptions that I have it in my memory, I will not change its form. But for example, here it becomes 5 over 6x squared, because 1x and x cubed are simplified, 2 of the x's are left here, 2 and 6 are simplified, it becomes 3 over x cubed. So I split it into 3 parts and then simplified as much as I can, but still it is not useful because I do not have these formulas in my table. This one exceptionally I have, so I would imagine this as what? This is also, by the way, very important. There are some examples in the book you need to understand. 1 over 2x means 1 over 2 times 1 over x. This you need to understand. You don't need to write it, by the way. I am writing it to make it clear for you. But here, I do not have that formula there, so you need to understand it in this way. This is 5 over 6. X squared is in the denominator. It is useless if I want to use the formula, the second row formula. So I bring it up. It becomes x to the power of minus 2. And the same thing here. So this becomes minus a third. And I bring x to the numerator. It becomes minus a third. In principle, I should also bring this up. The reason that I didn't do that, because I have it in my memory separately. If you don't have it in your memory, because I told you they are not in the formula sheet, you should also do this here. So you need to bring it up x to the power of minus 1. Okay, now the differentiation starts. 1 over 2 is a multiplicative constant, so I just write it down. The derivative of 1 over x is in the table, is minus 1 over x squared. And then 5 over 6 is a multiplicative constant. And then I apply the second row formula for this. So minus 2 goes down, x to the power of. I subtract 1 from the exponent. minus 2, I subtract 1 from it, minus 2 minus 1 is minus 3. And then minus a third is a multiplicative constant here again. I do not touch it, I just take the derivative of this part. Minus 3 goes down according to that rule. X to the power of 1 unit less, minus 3 minus 1 is minus 4. Differentiation is finished because you see there is no prime left, but you need to simplify as well. So let me just simplify that. So the t prime of x becomes equal to this minus positive. So when I multiply them, it becomes negative. 2 will be multiplied here. Of course, 1 will also be multiplied there. And this minus 2 here and 6 are simplified. 3 is left in the denominator. Positive, negative multiplied becomes negative 5 over 3. This becomes x to power minus 3. I prefer to write with positive powers, so I bring it back again. So this becomes positive 3. And then here, minus 3 minus a third. When I multiply them, it becomes positive 1. So I don't need to write it. And then x to the power of minus 4, I bring it back to the denominator. So this becomes this function. So this is the derivative of this function. I just remind you again, even though these functions are not that complicated, but if you really want to do the derivative of this function using the definition of the derivative, then you will realize that the calculations are really messy. So I just want you to understand, even though we started with some kind of guesswork or limits or something like that, but we are going beyond that. So it actually improves our capability of calculating derivatives tremendously. Okay, so one example that I want you to know about, this is not a new example, but this is the first time that I want to solve it in that way. So I will say that, okay, example, let f of x be equal to 2x squared plus 3 divided by 2 square root of x. Determine f prime of 4. So in the previous cases, I asked you to calculate the derivative of a function as a general function. But I am asking you to calculate not the whole derivative, but the derivative of the function calculated at 4. So, but this is nothing, but you have to do the process of finding the derivative first, and then replace the value of x in the derivative with 4. So, I mean, this is just one extra thing that you have to do. Okay, so let us just do this. If I ask you to calculate f prime at a given number, be careful, you are not allowed to put 4 first. You have to take the derivative first, yes? So how should I take the derivative? This function is not in my table, so I have to change its form. So first, the first thing that I do, I will change its form. Okay, now you have enough experience. How should I write it first? Yes? Yeah, separate it exactly as before, yes? So I would write 2x squared over 2 square root of x plus 3 over 2 square root of x. And I have to try to simplify it first, but simplification, I want you to understand how it goes. This 2 and that 2 are cancelled. I want to simplify. Let me simplify it here. I have x squared in the numerator. I have a square root of x in the denominator. So what should I do in general? X to power 2. This becomes x to power 1/2. But you already know that if I have 2 powers with the same bases, I write the same base and I subtract these powers. So 2 minus 1/2. 2 minus a half is 3 over 2. So this is why x to power 2 divided by that is written as this one. And then here, what should I do? Let me write it here as well for you. So 3 over 2 square root of x, you need to interpret it in that way yourself. Yeah, if you think you will forget, try to write all the details, okay? So this is the way you need to think about it. And then 3 over 2, and then I have 1 over x to power 1 half. Don't get confused. Don't say that I will not touch it because I have it in the formula. No. You have the derivative of the square root of x, but this is not the square root of x. It is similar to it, but it is 1 over square root of x. So you have to transform it. So you write it in that way, and then you bring it up. So this becomes 3 over 2 x to the power of minus a half. Okay? So this expression is equal to that one. So I will write it here. Now the function is ready to be differentiated. So I differentiate the function now. So 3 over 2 goes down. X to the power of 1 unit less. 3 over 2 minus 1 is how much? Is 1 half. And in this case, minus 1 half goes down. 3 over 2 being multiplied by minus 1 half is minus 3 over 4. And x to the power of 1 unit less. You already have minus a half. You subtract 1 from it. Then it becomes minus 3 over 2. Differentiation here is finished. But whenever you want to calculate it as a number, it is better to simplify it as much as you can, and especially write it in third form. So f prime of x is equal to, I would write it as a third form. It is easier for our brain to process it. And then here what I do, I will bring it down. This becomes positive 2/3, and this becomes the second root of x to power 3. So this is my derivative. When the derivative in its final form is ready, then you can calculate this number. So therefore, what can I do? I can write f prime of 4 is equal to, I replace x in my derivative with 4 everywhere. So this becomes 3 over 2 square root of 4, and then minus 3 over 4 square root of 4 to power 3. And then simplify that. Square root of 4 is 2. 2 and 2 are cancelled, so 3 is left. 4 to power 3 is 64. Square root of 64 is 8. 8 times 4 is 32. So it is minus 3 over 32. And then if you take the common denominator, so this becomes 96 minus that is 93. So this will be the value of my derivative. Yes? So remember, I have seen some mistakes like that. It is clear when they are asking you about the derivative at a single number, you're not allowed to put the number in, because you need to know the whole function f prime, which I did it here. Then I am allowed to replace x with that number. Any questions? Okay, I will give you one more example. This is not new, but I want you to change your perspective about how to solve the problems. But be careful, it doesn't mean that you can now forget about the definition of the derivative. Okay, no, because sometimes they ask you to find the derivative using the definition or using first principles. In those cases, even if you can manage to do it with these rules simpler, and even if it is correct, you will not get the points when they ask you to do it using the first principles or the definition of the derivative. Okay, so this example I want to mention is this. which is also a very important example, not because it is hard, but this was the motivation we started to talk about the derivative in the first place. So determine an equation to the line that is tangent to the graph of the function. Let me make it simple this time. The function f of x equals to x squared plus 3x minus 1 at the point on the graph whose x coordinate is 1. So that is just a famous example. We had this example before, but in the previous cases, there was only one way for us to do the derivative, and that was the definition. But if this question is given in the exam, you really don't have to do it, and it is better not to do it using the definition, use the rules. So, but this is, I want you to remember this picture in head all the time, because that's the most important one. So if I have a function, y equals to f of x, and if this point, which I call it the point of tangency, I want to draw a tangent line here. So if this point is A, if the x-coordinate of the point of tangency is A, if you want to find the k value is f prime calculated at A. So what I have to do, this is just a picture, not for this problem. This is always the case. So what I do, I will here a is 1 in this problem. A is given to you to be 1, the x-coordinate of the point of tangency. And then what I do, I will calculate f prime of x. So my goal is to calculate the k value. According to this picture, k value is f prime of a. But a in this problem is 1, so I have to calculate f prime of 1. But this is exactly the same problem we solved here. It's much simpler. So first you need to go and calculate the derivative. So the derivative of this function is extremely simple. You can do it in your head. This becomes just 2x. And the derivative of 3x is just 3. The derivative of 1 is 0. So that's my derivative. But I have to calculate it at 1. After I found my derivative, I replace x with 1. So let me write it. K is equal to f prime of 1, which is 2 times 1 plus 3, which is 5. So this means my k value is 5. Yes? The k value is 5, and then everything becomes clear. So what is the formula? I need to find the y coordinate, but the y coordinate is also simple, because if x coordinate is 1, I put it here. So this height is always f of a, yes? So the point of tangency has coordinates a and f of a. Okay, so what happens? So let me clean this and just write there. Okay, so what I can do, I can calculate f of a, which is f of 1. Instead of x, I put 1. 1 plus 3 minus 1 is 3. And then I have my formula, which is y minus f of a is equal to f prime of a times x minus a, or whatever you know. It doesn't matter if you really remember it in this form. So this becomes y minus f of a is 3, f prime of a I calculated is 5, and then I have x minus 1. I also prefer to simplify that, so it becomes 5x minus 5. I move 3 to the other side. It becomes minus 2. So that will be the answer to this problem. So we don't have to use the definition of the derivative. There is only one thing left for this lesson. There is no lesson actually. This is just different symbols that you see in different books for using derivative. I just want to talk a little bit about them. So mainly this is the notation we use, but in some books or even sometimes in your own book, you see different notations. So let us say that we have y equals to f of x. If I want to show the derivative, I can usually show it in that way, or because y is also equal to f of x, you can also use the derivative y prime. In more advanced book, you see d for d operation. This is the derivative operator acting on f of x. So if you see this one, that also means the same thing, differentiate f of x. And one thing that I want to emphasize is the Leibniz notation. So Leibniz notation is this. So if you want to differentiate this, you write dy dx. Okay, so dy dx means the same thing. And that's also motivated by this, because when I say what is the derivative is the limit of f of x plus h minus f of x over h. Okay, but do you remember what was h? So if a is here, a plus h is here. Do you remember when I was teaching you the notion of the derivative? This length is f of a, this length is f of a plus h. So if I ask you to calculate, so let me write x here. If I ask you to calculate the difference between these two, you are calculating the difference between these lengths. So this is the change in y coordinate. So this is nothing except delta y. Yes? And h is the change in the x coordinate. So h is nothing except delta x. So that was the motivation behind the symbol. So the derivative is nothing except the limit of delta y over delta x when delta x goes to 0. So probably that motivated Leibniz to write this as this symbol, dy dx. But there is something more into it. I want to talk a little bit about the Leibniz notation here. You see, if I give you this function, this is, by the way, listen to this very carefully. So if I give you this function y equals to, I give you two variables here, a squared, x cubed, they are multiplied. If I ask you to differentiate this without saying anything extra to you, by default, we take x as variable, a as parameter, constant. So when I don't say anything and I ask you to differentiate this, what do I mean? I mean take x as your variable. Okay, then it means a squared is a multiplicative constant. So it means that I will not touch it. I will take the derivative of this one, which becomes 3x squared. And then I have a squared, so this becomes 3a squared x squared. But usually you might say that, okay, this is a little bit confusing. How should I know that x is the variable? This is the good point about Leibniz notation. It emphasizes the variable. So in Leibniz notation, if I want to say this, I would write dy dx. But if I mean for some reason a is variable, then this is good to say dy dA. Okay? So when I say dy dx, I'm also telling you that take x as the variable. And when I write dy dA, I mean take a as the variable. So if I ask you to answer this question, you answer the same. Okay, but can you tell me, if I ask you this, what do you answer? It means that you need to change the role of the variable to a this time. and the next letter, which is x, should be considered constant. So what should I write? Can you tell me? If I ask you this, I want you just to know about this symbol. Mainly I don't use it, but it is good to know about that. So what should I write for this one? Yes?
2x to the third a.
Yes. This means that, this emphasizes that no, the variable is a. It means the other letter should be considered constant. So then this is a multiplicative constant. When I want to calculate this, I will not touch it. But then I take the derivative of this one as if a is playing the role of that x in my table. So 2 goes down, a. So you see that the answers are different. So this is also good about Leibniz notation. If you have more than one variable in your function, the Leibniz notation can emphasize which one is your variable and which one is your parameter, a constant. Okay, any questions? Okay, thank you.